Hello everyone. Today we are here to discuss on the topic optimization on graphs using decentralized reinforcement learning. We are a group of three people, Shivam Gupta, myself Monkesh Singh and Harshit Gupta. Before understanding the problem of maximum independent set, we understand what is an independent set. An independent set is a set of vertices in which no vertex is adjacent to each other. On top of this, maximum independent set is an independent set with maximum possible cardinality for the graph. This problem is a very popular NP-hard problem and has multiple uses in real-world applications. One application of MIS problem is graph coloring. Graph coloring involves assigning colors to vertices of a graph such that no two adjacent vertices share the same color. Maximum independent set provides a solution for finding independent sets which can be used to color the graph efficiently. Another application is social network analysis. In social networks, nodes represents individuals and edges represent the relationship or interactions. Identifying a maximum independent set helps in finding a set of individuals who are not directly connected but still have significant influence or independence in the network. Another application is resource allocation in computing systems. In distributed computing systems, resources like processors or memory modules need to be allocated efficiently. Maximum independent set can help in allocating resources in a way that minimizes interference and maximizes overall system efficiency. So there are a lot of solutions available for maximum independent set. Some of the available solutions are exact solutions. An example of exact solution is branch and bound algorithm, which systematically explores the solution space by dividing it into smaller subproblems and cutting off branches that cannot lead to an optimal solution. Another exact solution involves DP, dynamic programming, which keeps on storing the data from graph and uses this memorization process to improve the efficiency of the algorithm. All exact solutions involve non-polynomial approach and can take a lot of time to solve, even for a normal graph. To tackle this, we have approximate solutions available, which find the correct solution with some probability. One approximate solution is greedy algorithm, in which the algorithm chooses nodes greedily to include in the solution set. Another solution is local search algorithm, which start with an initial solution and iteratively improve it by making local changes. Now coming back to our solution for maximum independent set, we are going to discuss a paper in which we are going to look at centralized algorithm involving reinforcement learning. The name of the algorithm being used in the paper is learning what to differ. So this paper sees the solution for the maximum independent set as a Markov decision process. The solution being presented in the paper is also an approximate solution. to the maximum independent set problem. What our algorithm will do is that it will generate multiple solutions to the problem and we will pick the solution which involves the maximum number of nodes or say maximum cardinality. First, we understand the states of the MDP. Each vertex in the graph can be seen as an included vertex, excluded vertex, or a deferred vertex. A state represents a vector which keeps a record of each vertex in the graph. A deferred vertex is a vertex on which an action will be taken. That is, either convert it into excluded or included vertex. Each MDP is initialized with all deferred vertices. An episode ends when all the deferred vertices turn into either excluded or included vertices. Next, we are going to understand the actions possible in the MDP. For each action, a set of deferred vertices is chosen, and each vertex is set to either included vertex, excluded vertex, or not change at all. It is important to note that the actions can only be taken on deferred vertices, and the included and excluded vertices are fixed for rest of the episode. Coming to the transition phase, it can be divided into different phases. The first one is update phase. The update phase modifies the graph as per the given action. After the update phase, we have the transition phase, which takes care of the conflicts caused in the update phase. Any conflicting vertex is turned back into a deferred vertex, and the decision for it is to be taken in the future. Also, if there is any deferred vertex next to an included vertex, it is turned into an excluded vertex. In this given diagram, an action is being taken on the given initial state. After the action is being taken in the update phase, the transition phase sees two conflicting vertices. These two conflicting vertices are being shown in blue and being converted back to deferred vertices. We can also see that the deferred vertex next to the included vertex is turned into an excluded vertex. Now, when the graph reaches the terminal state, the solution can be improved by using the two improvement local search algorithm, in which one vertex is being removed and two vertices are being added. We keep doing this until no more improvement can be seen. Coming to rewards, we define the reward at each state as the difference in cardinality of initial and final state. By doing this, the total reward is same as the final cardinality of a graph at the terminal state. As discussed earlier, we are going to sample a lot of solutions and we are going to select the best one of them. Therefore, we want the solutions to differ as much as possible so that there is a high chance that there is a solution which is better than all other solutions. Here in the paper, there is an extra reward being given to motivate this randomness. To do this, we make two copies of our initial MDP. In each copy, the agent works independently and chooses an action. We define the deviation between the coupled solutions in terms of L1 norm. The value of this diversification reward is being given on the screen in terms of RD. After looking at MDP dynamics, we begin with training. But let's first look at proximal policy optimization, which is being used in many top AIs like ChatGPT. PPO is an optimization algorithm which belongs to the class of policy gradient algorithms that directly optimize the policy function to maximize the reward. Unlike value-based methods that learn value functions to estimate the expected return, policy gradient methods learn policies directly by maximizing the expected return. In our case, PPO represents the policy function as a parameterized policy in form of a neural network, where the parameters are adjusted using gradient ascent to improve performance over time. Gradient ascent is an algo which is used to find the maximum of an objective function by ascending the gradient of the objective function with respect to policy parameters. The objective function is being used to train the model parameters. We train the model such that the value of objective function gets maximized. Finally, the algorithm outputs a stochastic policy which provides probability to take every action in every state. As we discussed earlier, that PPU formulates a parameterized policy. So in our case, we have done this using policy network and value network. The policy network in PPO takes the state observations as inputs and learns the optimal policy, which is the mapping from the states to the actions. On the other hand, the value network takes the state observations as input and estimates the expected return or value of being in a particular state. Both these networks use gradient ascent to update their parameters as discussed earlier. Both the networks work together with policy network providing feedback for value network and value network providing feedback for policy network improvements. Finally, getting to the training part, the MDP in the paper is trained using PPU. The PPU algorithm in paper is based on the actor-critic training following the graph-sage architecture. The term actor-critic refers to a hybrid architecture that combines elements of both value-based methods and policy-based methods. It's a popular approach used to address the exploration versus exploitation trade-off and improve learning efficiency in reinforcement learning tasks. GraphSage, full form Graph Sample and Aggregation, is a popular architecture for learning node embeddings in graph structured data. The parametric transformation in the paper is as shown on the screen. Objective function being used to train the model parameter. The objective function uses a clipping mechanism to limit the size of the policy update. This clipping mechanism is necessary to prevent the policy from sudden policy changes. This ends our discussion on the first paper. Now we will take a quick look at the next paper. This paper talks about the fast link rescheduling in wireless networks. The link for the paper is being given on the screen. Moving next to the problem statement. Let's assume we have two pairs of wireless devices communicating within themselves. If they interfere with each other while communicating, therefore, only one of the connections can be made to share information, while if we can expand this to a large scale with multiple pairs of devices communicating with each other, then there can be multiple interferences. Then we need to select links that can communicate simultaneously without interfering other links. At the end, we need an algorithm which will select the set of high utility links and allow them to communicate, while others are stopped from communicating. We will now convert this problem into a conflicting graph. Each vertex of a graph will represent a link between two devices, and H represents an interference between two links. We define a variable RKT defining number of packets that can be transmitted. We also involve the channel fading effect in which there is a probability of some packets being lost. Therefore, we choose RKT to be any value between 0 and max transmission rate allowed by the link. We also define a variable QKT which denotes the length of the queue at the kth link. Finally, we define utility of a vertex UKT which is the product of RKT and QKT. Our main aim is to maximize the delta hat T. Like the previous paper, we can formulate this problem to find the weighted MIS for the graph formed. Each vertex has a label of -1, 0 or +1 which represents not included, undecided or included vertex respectively. The state space, action space and transition space remain the same as the previous paper. The problem is solved by off-policy regularized deep reinforcement learning. We can design an off-policy algorithm where a prior policy is used to generate the current actions and they are used to train and improve the current policy. A regularizer is used to make sure that the prior policy do not have much variation when compared with updated policy. With this, we complete our discussion on the second paper. Now we move to the third paper. Until now, we discussed only the centralized solutions for the MIS problem. But now, we will talk about how we can make a decentralized approach to the maximum independent set problem. This paper talks about a parallel algorithm approach for the problem. The link for the paper is being shown on the screen. The paper starts by explaining a very simple solution for the MIS problem. For a given graph G, we define the set of vertices as V. We initiate two vectors, vector I and vector V dash. The vector I will keep the vertices which are going to be a solution for the MIS problem. The vector V dash is initially the collection of all vertices present in the graph G. At every step, we choose a vertex V and add. In this case, whenever we choose two vertices which are adjacent to each other, we select the vertex with lower degree to be added to I. Next, we remove all the neighbors of the currently selected vertices. We keep doing this until the set G dash becomes empty. This gives the final answer for maximum independent set problem as set I. With this, we complete our paper 3. Now, about the future plans, we have to make a decentralized approach. To make this happen, we have to go for a multi-agent reinforcement learning approach. There are many cases where multi-agent reinforcement learning can have significant benefits over single-agent RL algorithms. MARL can decompose a large, intractable problem into smaller, trackable problems. There are multiple examples for the use case of multi-agent reinforcement learning. Suppose there is a factory where goods are to be transported from one place to the another. If we need to work more efficiently, we need more number of robots to be working in the transportation. In this case, a central agent may not be able to track the movement handling and collision of robots with each other. In such a case, MARL can be an effective choice. It can help the robots to take care of their individual movements and communicate within themselves locally to prevent any collisions. This way, multi-agent RL can be a better choice over single-agent RL. We can take another example to explain. A single agent may not be able to manage driving a vehicle smoothly and preventing collisions on roads simultaneously. Here also, a multi-agent RL can be a better option. The agents can work in themselves for better vehicle control and communicate among themselves to prevent collisions. Here, each agent can work with its own observations and contribute to the overall reward for environment. In our case, we have a large graph to find the maximum independence and give better results than a centralized solution. But as we take the graph to a bigger scale, the centralized solution becomes less effective. In large graphs, the multi-agent approach can help move to the solution faster. Each agent can work with their own set of actions and states and take care of collisions with each other when needed. Over this, multi-agent approach has another benefit. In case of failure of an agent, other agents can still keep working on the problem. This makes the multi-agent approach more robust and less prone to failure. On the other hand, a failure of agent in centralized solution can lead to a direct failure of the solution. We still have to decide if we need multiple agents to work together or independently. How many agents do we need and what are the different multi-agent models and their optimal policies? With this, we conclude our presentation on optimization of maximum independent set problem. Thank you and I hope you like the presentation.